After pigeonhole principle, there is one more technique that I want to show, and then this technique is proved by construction. Sorry. So proof by construction is actually nothing special. You just want to show something is true or something exists by giving an example. You construct an example, and that's it. So this is called proof by construction. So let's see some interesting examples. Okay. So as long as when you want to show something exists and then you can give an example, then that's good. So for instance, okay, so let me define something called a k-regular graph. So k-regular graph. So what is a k-regular graph? So it is a graph such that each vertex has degree k. That's it. Okay, so for instance, this one is a 2-regular graph because for each vertex the degree is 2. Is that okay? Does that make sense? Okay, so this is a 2-regular graph. Okay, so maybe we can have 3 regular graphs, like what? 1, 2, 3. 1, 2, 3. Maybe this one. 1, 2, 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Oh, that's 4 here. Maybe this one. Okay. This one is a 3-regular graph. Is that okay? So because for this graph, every vertex has degree exactly equal to 3. Is that okay? Is that okay? Okay, so here this theorem says, show that for every even integer n, there exists a 3-regular graph with n vertices. Okay, so I need to have restriction for every even n, and then let's say n is greater than or equal to 4. This is my theorem. Okay, so when n is equal to 4, then this is an example. This is a 3-regular graph with 4 vertices. So this is a case where we have 6 vertices, right? And then there is a 3-regular graph for 6 vertices. Is that okay? Then, but then this theorem says n is any even number greater than 4, greater than or equal to 4. Then you can always find a certain 3-regular graph. Yeah, then what? Then what should we do? So here, so we are not going to prove it true so that for every n you draw a graph for me, because it will run out of time. It would be much better if you give us a strategy such that when you have an even n, then how we can always draw a 3-regular graph. Okay? Okay, let's see. So let's say we have 8. So 1, 2, 3, 4, 5, 6, 7, 8, right? Well, to get 3-regular, let's make it simpler. Let's make a ring first. This candles for 2, okay? So if every one of them can get to make it 3, then it will be done. So what is the best way? So each one needs to find a friend. Yeah, there are many examples, many ways, but the best way for me is, okay, everyone, you have an opposite vertex. You join to your opposite vertex. Then this is a 3 regular graph. Is that okay? Yeah, I like this, yeah, okay. Okay, so whenever you have even number of vertices, let's say 10, so you arrange them in a circle, form a ring, and then each vertex you join an edge with your opposite. That's it. Then this is one of the 3 regular graphs with n vertices. Is that okay? So this is so-called proof by construction. You construct an example, or you construct a strategy so that it helps you to find what you want always. Okay? Okay. Let's have another one. Okay. Now this one is a strange example. It is something people call non-constructive proof, but I still classify it as construction, proof by construction, because we still need to somehow to construct things. So let me tell you the example, the problem formulation. So this problem says, show that there exists irrational number Q and R such that Q to the power R is rational. Wow, amazing, right? So you have an irrational number, you have another irrational number, right? But somehow, Q to the power R is rational. Is it amazing? Yeah, I think this is quite amazing. So there are 2 proofs. One is non-constructive. So I will show that to you first, and then let's see another way, which is constructive. So this is proof 1. Okay, the first proof that we have is, let's take a look at this number, square root 2. So we know square root 2 is irrational, right? We have proven this last time, to the power square root 2. So this is a number, right? This number to the power square root 2. Strange. Everything is strange, very, very strange, right? But what is it? Although this number is very strange, so what is this number? So you have a number a to the power b to the power c. This is actually equal to a to the power bc. Is that okay? Yeah, look, let's say c is 2, okay? So you just have a to the power b 2 times. So you get a to the power b plus b, so a to the power 2b. So in general, a to the power b, this number to the power c, is just a to the power bc. Okay, so here, this is equal to square root 2 to the power square root 2 dot square root 2. And this is equal to square root 2 to the power 2, 2. Good. Okay, well, is it done yet? Have we proven this theorem yet? No, we have not proven the theorem yet. Reason, okay. Now this is rational, right? But we don't know whether this is irrational or not. We don't know. We want to find irrational to irrational such that it is rational. Okay, I know that the resulting thing is rational here. You have this number to the power this number is rational. But this could be rational. This may not be what we want. Okay, now, but amazingly, whether this is rational or irrational, we are happy. If this number, square root 2 to the power square root 2 is irrational, then we have irrational to the irrational rational. Is it okay? And what happens in the opposite case? In the opposite case, when this part is rational, then we cannot have a direct result. But then we will have what? We will have square root 2 to the power square root 2 is rational. Is that okay? Okay, once again, okay, there are two cases. Case 1, this is irrational. If this is irrational, we are immediately very happy. We set this as Q, we set this part as R. Okay? On the other hand, if this is rational, then what will happen? Then we will set square root 2 as Q, and then set this square root 2 as R. Then we will still have irrational to irrational equals to rational. Okay? Let me write down, okay, more clearly, okay. Okay, now, so there are two cases. So case 1, square root 2 is irrational. Then in this case, we are happy because we set Q to be square root 2 to the power square root 2, and we set R to be square root 2. And we are very happy. Because we have Q to the power R is rational. And each part is irrational. Okay? And how about case 2? Case 2 is square root 2 is rational. Then in that case, we set Q to be square root 2. We set R to be square root 2, and then we are also happy. Because this time, square root 2 is irrational. Square root 2 is irrational, but square root 2 is rational. So in either case, we will be happy. So that means that the theorem is correct. If you are okay with this, could you please raise your hand? Okay, now, but somehow we are a little bit sad because we have done so many things, we still don't know whether there is an irrational number to the power irrational is equal to rational. We don't get the number. So there is an alternative proof. So this time, so we call this a non-constructive proof because after we've done a lot of things, we still don't know what is the value that you want to set as Q and what is the value that you want to set as R. You don't know, okay? But let's take a look at another example. Okay, so let's try the other example. Let's see if my memory is okay. So let's got proof 2. This time, let's take a look of this number, square root 2. Square root 2 is irrational, right? Okay, now I have another number for R. So this is log of base 2, 9. Okay, we will later show that this is irrational. But at this moment, let's check out what is square root 2 to the power log 9. Okay, so something like this. You have A log B. It is always equal to B log A. Is that okay? Reason, you take log. So you got log B times log A here. You get log A times log B there. So after taking log, they are the same. So they must be the same. Is that okay? So square root 2 to the power log 9, it is equal to 9 to the power log 2 square root 2. Is that okay? And then what is it? So this is 9 to the power 1/2. Square root 2 is 2 to the power 1/2, right? So this is equal to 3. Rational. So now, it remains to show that this number, log 29, is irrational. If you can show that, then done. Okay, and it's not difficult. We prove it by contradiction. Okay, so assume to the contrary that log 9 is rational. So if it is rational, then log 29 you can write it down as P divided by Q. Is that okay? Is that okay? For some P, Q integer. Okay? Is that okay? 2 power of them. So you get 9 is equal to 2 to the power P over Q. Is that okay? Is that okay? So what do we have? So you get 9 to the power Q. Q is equal to 2 to the power P. Is that okay? Is that okay? Integer. Then we get contradiction. Left-hand side is odd. Right-hand side is even. So odd cannot be equal to even. So you get a contradiction. Is that okay? Okay? Oh, of course, you can get odd here unless P is equal to 0. Yeah, but you see that P cannot be equal to 0. So P cannot be equal to 0. Q can also not be equal to 0. So Q cannot be 0 because it is the denominator. P is not 0 because the number log 29 is not 0. Okay, so we should not set P to be 0. Is that okay? But in that case, you get this one is odd. This one is even. So odd cannot be even. So you get a contradiction here. So the contrary is wrong. So that means that log 29 is irrational. Now, so using this proof too, we really get the irrational to the power irrational. It is equal to rational. Okay? Good. So that's it. Okay. So we will have our homework 3, right? Deadline this Thursday. So Simon will give tutorial on that day. And if we have time, there's a little bit more proof by construction example that I want to show. Okay. So otherwise, we will talk about the lecture next week. Okay. Thanks. Okay.